And so I would like now to invite the audience here and online to ask questions.
There are a couple of questions
Oh,
online
okay.
already. Yeah.
So, wow, this one?
Yeah.
Okay.
I'm Rosinski from FEMA.
Okay, so I will start with just a question from the audience online. So I will read it. Earthquakes are not climate-driven disasters, but some of secondary impacts might be influenced by climate change. For example, persistent drought, heat waves, wildfires, increased frequency and intensity. El Niño atmospheric river could impact fire following earthquake and liquefaction, rising groundwater. In addition, embodied carbon from earthquakes damaged building is also gaining attention. Are any of the studies use cases looking at how earthquake simulations can help quantify, estimate the connection between climate change and earthquake impacts? Yeah. I ask because climate change resilience is a social priority, and the ability to link earthquakes losses, hazard damages to climate change is a pathway to obtaining earthquake mitigation funding. Long question, interesting question. Anyone?
I'll provide an answer. I think, I mean, yes, it's an urgent problem that we all need to address. And so I think right now the Sim Center tools we have allow you to do the earthquake part of it, and you can take that output and then use it for what you want in terms of climate change effects. So we have some users, for example, that we're starting to work with now who do landslides, and you have earthquakes, then you have rainfall, and then you have landslide, and the amount of rainfall is changing because of climate change and all of these things. So that secondary impact of landslides is changing due to climate change as well. So those types of things, people are using our tools to do those. I think we'll shift our focus in the next years to try and integrate that more directly.
In terms of buried infrastructure, I think Matt mentioned about landslide, but also the groundwater table is rising because of that effects, and that has a huge consequence on how we're going to deal with our buried infrastructure along the coast, and how that influenced by when the earthquake happens, there'll be liquefaction and all these things. So it's a totally new, but like I showed you some of the distributed fiber optic sensing, we can use DAS, and DAS can be do geophysics. We have some work on looking at where's the ground table using this distributed fiber optics. So by looking at sort of how the distributed acoustic signature doing some geophysical methods, we may be able to find where the groundwater table is more accurately rather than drilling a borehole.
Marco, you wanna have anything to add, or? Oh, we cannot hear you.
I don't know if you can hear me. Well, could you hear me? Okay, so now it works. Just a quick comment. So on my side, adding to what has been previously said by Professor Soga, in reality, clearly, if the water rise, there might be a connection with eventually the increased liquefaction risk in certain areas. The other thing that I can think about, at least from an insurance perspective, is clear that out of the climate change and eventually the idea to reduce, again, this effect, you can always put together the two things of retrofitting and making the buildings at the same time also more efficient. So I think that this is one of the major efforts that actually we're going through, trying to put together these two things in order to enhance also from a seismic perspective, and on the other hand, basically from a climate change, so reduction of the CO2 emission.
Great, thank you. So we have one more question from just the audience online from Professor De Jong. So what spatial resolution did you use for the input of simulated ground motion data from the Lawrence Livermore National Lab SW4 Hayward scenario?
Ooh, Frank? Resolution? Jinyan?
That's an older vintage, so the frequencies were probably relatively low, I think. So it's probably, you know, the data set was probably tens of meters, most likely.
Most likely, yeah.
Yeah, that was quite a while ago. You know,
Yeah.
the resolution is much higher now. So, you know, at 10 hertz with 140 meters per second on the Hayward Fault, the grid spacing is 1.75 meters at the surface.
Yeah, I
More
mean,
than you could use, probably.
from our perspective, it's a grid, right, that we map nearest neighbor to. So whatever grid you can provide is what we can put into our simulation.
Okay, We hope this provides the answer to the question. And do we have any questions? Yeah. Probably, let's see. Do we have the microphone? Or maybe you can
Yeah.
just come here, okay.
Come on over.
Have a seat.
This is a question to Marco related to the slide he showed, of course, the magnitude distance slide. If we can take a look at that again, I have a question on that slide. The past earthquake data that showed the magnitude versus distance, recorded events.
Marco's presentation.
By the way, we're unable to hear you, Marco, but
Oh,
I think you can hear us.
okay. Now it works?
Yeah.
Okay, I was listening to what you were saying, but I didn't capture exactly which slide you were referring to.
You showed a slide where you were saying we are missing near fault recordings. There's a gap in the data, and you isolated a region of your plot, the top left corner of your plot, that showed the magnitude versus distance recordings, historical recordings. So I wanted to ask a question about that slide.
Okay, let me see a second. I'm trying to share again, but actually it's going to be a little bit complicated. So I remember the slide. I don't know if you can make your comment even without it. Or...
If I remember correctly, the slide, I've seen different versions of the same elsewhere as well. The data really starts disappearing, you know, within, say, 5 kilometers or 1 kilometer. It's very narrow. Like within around the 10-kilometer range, there's actually quite a bit of data, it seems. It's not, of course, as large as, you know, 50 kilometers, 20, 30, you know, that end. But it's not super rare for the 10-kilometer and a little bit above that. Do you really need that narrow band of data from around the faults that are within a few kilometers of it? Is that important for the insurance purposes? I'm wondering.
Yes, so I guess I'm missing you. Sorry. Hear me now? Could you hear me? Could you hear me? I cannot hear anyone anymore.
Right? Yeah.
Hear you back again?
Yeah, just I think the very end of the last part of your question.
So, yeah, Marco, I was just wondering how important it is really to your work, insurance, reinsurance work, that missing data that physics-based simulations could fulfill. How close do you really want to get to the fault, is my question.
Hold on a second, we cannot hear you, Marco.
So, yeah, only one you can do. So once you finish the question, hand it off and he will
Okay,
answer.
he's done with the questions.
Yeah, so
And we still can't hear.
we still
Now, could you hear me?
Good. Yeah.
Okay. So the point is just the following. One point is how close we need to be, basically. So how well we have to represent, or we need to represent near field, the very near field to the fault, is one question. The other thing is actually, and I hope it was stressed clearly, the special correlation between the different ground motion. This is something really crucial, because you have always to think that what we got in mind is actually always a portfolio. So we are always doing basically analysis, or I would say most of the time, analysis that are related to a distributed portfolio. So in a nutshell, yes, it matters to us. I'm pretty convinced, yes, because we clearly see that defining properly that area allows us to have a quite good view on what is going to be the final loss in our portfolio and how it can change from different realizations. So in a nutshell, I think it makes a lot of sense, yes, and one of the good tools that we got now is actually physics-based scenario in order to determine something like that. And just, for example, referring to the very recent event that was affecting Japan, if we take a look at the area, even in spite of the very dense network, KickNet and KNet, what we got in that area are, let's say, some dozens of stations that really monitor the near field area. But that's all. So I think that an improvement there will significantly change our view on the final estimation of the losses.
All right. We hope this provides the answer to your question. Great, thank you. Thank you so much. Unfortunately, we don't have time for more questions unless we have some burning question from the audience here. But, oh, yes, okay. One last question from Professor Smirzini. You want to come here? It's probably better.
A quick question for Professor Soga. Thanks a lot for the very nice presentation. To estimate the impact on the water supply system due to earthquakes, the seismic fragility curve is an important component, and in your presentation you mentioned fragility curves for peak ground velocity. Of course, pipelines may be vulnerable to other effects, lateral spreading, fault, offset, and so on. So I would like to ask you, in your opinion, which are the main research needs to advance, to enhance seismic fragility curves for pipelines in view of application for regional scale risk assessment to water supply systems?
And that's a great question, and we use PGV on that particular work because it was readily available to do so, and there's some. But then the peak ground displacement, PGVD, is also important. So in OpenSRA, there's a tool that we developed together with Professor Bray, who led that, is open seismic risk assessment tool that commissioned by the California Energy Commission, which Sim Center has that tool, and that's looking at the PGD as well. So we have developing that tools in that case. But the issue also is that, you know, as every people are different, every pipe is in different conditions, soil condition, and all these environmental impact, their traffic loading is different. So at the moment, what we're trying to do is to figure out a little bit more using statistical and data analytics to figure out how each individual pipes, how they're different. And with more data sets, we'll be understanding that. So it goes both ways. One is understanding the importance of different peak ground A or V or D, but at the same time, really characterizing our materials better. But also trying to, as my colleague said, trying to see the monitoring to be more important as well. But thank you.
Thank you.
All right, so thank you, everyone. And once again, join me in thanking our speakers for their great talks and also just answers to our questions.